And welcome back. Today we're testing the amplifier, the Class A 807 push-pull blah 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 amplifier, and we're testing it with a difficult load. We're testing it not with a dummy resistor, we're testing it with a dummy capacitor, and this is the result. The input is grounded and we are getting it oscillating at 1.3 volts RMS and 190 kilohertz ish. So obviously that's no good. Let me turn this off. So as you saw the other day, I was playing music for it when it was connected to those Mission 720 speakers. No problem whatsoever. No oscillation problems as far as we could hear, or could, you know, it might have been oscillating. I mean, but 190 kilohertz, we can't hear that. So the reason that I put a capacitive load on it is to test it for stability. We want to be able to connect this amplifier to pretty much any speaker without it going unstable. And that means we've got to put a few sort of RC networks in place to create high pass filters such that at a certain cut-off frequency the RC network will attenuate any frequency above that. So in that case we've got 190 kilohertz. On our frequency sweep that we did, it was pretty good up to about 60 kilohertz. So, and it started to roll off about there. So how about putting some RC networks in the amplifier so that at 60 kilohertz it attenuates any frequency above that, and we can do that in different ways. Now as you may know, I'm not the be all and end all about amplifiers. I just mess about, knock amplifiers together, and they sort of work. And you know, I don't know everything. I'm not an expert by any means. So there are different ways of doing this. This is our preliminary sort of schematic. This is our output. Here we've got our 500 volts going into our output transformer. Yes, that is supposed to be an output transformer. Obviously this is just one side of the push-pull. The output transformer winding from here to the anode is 18 ohms. We could use that resistance of the windings as part of an RC filter, and we can stick in, I've worked it out, it needs something like 150 nanofarads, but we could stick in a capacitor from this HT point to ground and see if that does the job. I've not tried this before, so let's try that and see what happens. Right, well okay, that hasn't worked. Let me turn this off. You can see there, look, as I turned it off it was jiggering about. So what I did, this is 500 volts going in here. I put a 100 nanofarads or 0.1 U to ground. That didn't work. So I'm going to try what we usually do, and that's to put, mind you, I could put a bigger capacitor in there, but no, I don't think that's what we need. I'm going to put an RC network across here and then see if that does the job. So there's a couple of resistors and capacitors just tacked in. This is our anode, sort of lead going out to our anode caps down there, or up there should I say. 1k resistor to ground, 220 picofarad, no sorry, 2N2 or 2200 picofarads going to the anodes. Let's see if that works. Alright, startup initiated. We just got to wait for the bugger to for the soft start to click off, should I say. what's going off frequency wise. It's just trying to make up its mind. I don't know, I've got 12 volts, fuck me. Right. And that's saying that it's at 13 Hertz. 12 volts at 13 Hertz. Okay, and that's obviously, so we've gone the opposite way. It's cured the high frequency oscillation, but now we've got low frequency oscillation. This is going to take some thinking about. One moment. Here we are some days later. I haven't touched this amplifier for a good few days, and as I remember where we were with the 100 nanofarads, if I can point you at the back there, with 100 nanofarads capacitor as our load instead of a dummy load, the amplifier was oscillating, self-oscillating, parasitic oscillation, whichever you like to call it, at 190 kilohertz. To stop that, and this is with feedback, negative feedback applied. To stop that, we put in these couple of 1K, big 1K resistors, and I think these are 2200 picofarad capacitors. So they're going from anode to ground, and they basically form a high pass filter with a cut-off frequency of about 70 kilohertz, meaning everything over 70 kilohertz, woof, gets attenuated. But then we had the problem that now it's self-oscillating at 12 hertz, so we've gone from the top end, so we've gone from high frequency instability to low frequency instability. What can we do to try and solve that? Do we need to even bother? This amplifier I intend to use for my own sort of personal use. I'm not going to sell it. It's probably going to be on the same speakers, you know, all the time, those Mission 720s. And so it's quite happy, you know, with those speakers. It's stable. But still, we ought to at least try to make it unconditionally stable, didn't we? You know, do the job half right. You don't see this on a lot of amplifier builds. That you know that people build. They sort of get it running and it works, and then that's it. But having read Patrick Turner, this guy in Australia who is no longer with us, died last year, or was it this year, I can't remember. He basically went to great lengths to make his amps unconditionally stable, and talking to him via email and things, I can see where he's coming from. So what can we do? We need to do a bit more testing, but to do that we need to go back to sort of first principles, as it was, and test this without a load, without any load whatsoever. And as a lot of people will tell you, valve amplifiers, you do not power a valve amplifier up without a load. Why? If without a load, there is no load reflected back onto the anodes of the output valves. So basically this the voltage, the HT voltage and the voltage on the anodes can shoot right up to thousands of volts and destroy the output transformer, output output valves, you know, and just to basically ruin your day. We've got 3 reverse bias diodes to stop that if that should happen, but also we're not going to be testing this at full whack. We're going to be testing it very, very low with the output power. I'll go and set that up and then we'll have a look at the scope and everything. Right, as you can see, there's no load on there. Just pulled that away from the output terminals. I've got my scope on the positive of the 8 ohm tap, should I say, of the output transformer. The other wire of the output transformer secondary is going to ground, it's tied to ground, and we have unsoldered the negative feedback going into the V1 or the gain stage of the amplifier. So we've got no load. We've got no output coming from the HP 8903B. We're monitoring the output on the scope. So we shall power it up and see what happens if for any reason that it starts like going mad. We shall shut it down. So basically it's at less than zero, you know, I don't know, minus 24 dB or whatever. I haven't worked it out because my bloody calculator's broke. Power's on. Monitoring the bias here. Bias of one valve and, well, where are we? The higher figure is the bias across one valve. This is the negative bias being applied, and as you can see, we're getting some nasty, horrible waveform on the output at 1.4 volts RMS, and that's at 146 Hz. Okie dokie, we have got some improvement. We've now got that, which is 150 Hz sort of thing at 24 milliamps, which is an improvement. So I'm going to turn that off and see what I've done. The first thing I tried was a low frequency shelving network, which is that. So here's our coupling capacitor, which is that yellow one there, which is a 10 nanofarad, I think, capacitor. Let me just make sure of that. Can't see a frigging thing. Yes, 10 nanofarads. So at first I tried this shelving network, which is a 1 meg and a 47N, which basically, as far as I know, I mean I'm not totally au fait on this, that creates a low frequency shelving network with a cutoff frequency at 3.39 Hz. So basically what it's doing, that's sitting between the gain stage and the phase splitter. There we are, there's the two components in question, and it's attenuating everything under and sort of either side of about 4 Hz. So hopefully that should stop the low frequency instability. It didn't. So next I tried some big capacitors, biggish capacitors. They're a couple of 47 microfarad 450 volt. I tried those from our 500 volt input to ground, and I tried some more decoupling here, which is a 10 microfarad 350 volt from the screen grid supply to ground. That didn't work. So then in the end I thought, right, well let's have a look at the gain stage. Now then, somebody gave me these really nice sort of 1000 mic caps, 10 volt caps a while back. As you can see, I think the Panasonic gold thingy dude is 105 degrees. I had one of those as my cathode decoupling cap on the gain stage, which is madness. You wouldn't normally get anything as big as that. So I took that off and put 100 microfarads on there, and they basically, what that has done, that has reduced a low frequency gain, and that more than anything is responsible for better low frequency stability. The reason I tried the decoupling capacitors is because basically we've got a power supply here, we've got a long cable running all the way to here. That is far from ideal. In valve amplifiers we want all our wires that joins anything, but particularly power supply wires, we want them to be as short as possible, not 3 foot long, which is the case here. So normally what you would do, I think, in this case is to put a capacitor at the end. It's a bit like putting capacitors on across the power supply inputs on an op amp. Yeah, so anyway, that didn't work. Reducing the gain of the front end did. So now we've done that, so we've sort of improved the low frequency stability. We've sort of killed the high frequency stability. So what I'm going to do now is I'm going to connect the capacitor back up without the negative feedback applied, and then do a frequency sweep across that. I'm going to leave these decoupling caps in for now, although they're less than perfect. You see we've got more stray capacitance and inductance with these big long leads. More later. Okay, now we've got some new madness. It's now, we're back onto a capacitive load, and we're now on, what was I saying, 13 kilohertz at 12 volts. This is something I've not come across before. So what I'm doing, I'm scoping the power supply going to the 300 volt regulated power supply going to the screen grids. So see, it stopped. So we've got like a sawtooth, yeah, which we shouldn't have, and then we've got this boingy. Oh, now what's that? That's 1 second. That's very low frequency oscillation. It's the next morning now, and I just unsoldered this decoupling cap, and what I noticed was that possibly, see that joint there where the scope's on, I thought, hello, is that touching the bloody cathode? Could that be causing the issue? Let's pull that up and see if it goes away. The answer is no. Now look at this curious behaviour, look. This is the screen grid supply. Screen grids. I bet it's not going to do it now, is it, little fucker? Come on. There we go. So we sort of get a bit, I mean, there's two issues here, look. I'll show you. Hope this isn't boring TV. So we've got the boingy boingy, the oscillating, which seems, there we go, 1, 2, 3, 4, 5, 6, 7, 8, about 5 or 6 scans, which were we on, 50 milliseconds per thing, so it'll be 50 milliseconds, we get that, oh that's about 250 milliseconds, no, what am I don't know, you get the idea, look, it stops. So we've got two issues. We've got the sawtooth wave when it doesn't want to be. That could be, I don't know if you can see that with the camera. See that? That's interesting. See that? See this, where do you call it? Voltage reference valve. See how that's glowing? I don't know if you can see it in the camera. It's glowing bright. It's blinking on and off. It's varying in intensity, the light. Then it stops. Then it goes again. And that, I'm keeping one eye on this valve, one eye on the scope display, and that corresponds with the boinginess, the instability. So one thing I thought, right, so we've got two issues. We've got the instability and we've got this sawtooth wave. We shouldn't have this, it should be flat. Okay, some improvement. We've stopped the boinginess This is the output of the 300 volt regulated power supply. I've solved that by putting this capacitor. I'll show you where I put it in a minute because I need to turn this off. Okay, here's the schematic that I took this off, based the regulated supply on. You see here, this is our output from a series pass regulating valve. We are using a 6080 instead of an EL34. As you can see, they've got a 2 microfarad cap going from the output of that, basically our 300 volts in this case, to our control grid of one part of the the error amplifier. I haven't got a 2 microfarad, so I've used a 10 microfarad 350 volts. That seems to have stopped it. You can see here he's using the Zener for his voltage reference. We're using a VR150, but for some reason it's a VR100. As you can see, you've got a couple of caps here, decoupling caps. This is an STC valves voltage stabilizers application report. Tells you everything you need to know about, pretty much everything you need to know about voltage reference valves, voltage stabilizer valves. These are impedance frequency characteristics. Now then, if we go back a ways, there we go. Impedance frequency characteristic. The variation of stabilizer incremental impedance with frequency has already been mentioned in sections blah blah blah. The general practice of shunting the stabilizer with a capacitor not only introduces the danger of relaxation oscillation, but also results in a parallel tuned circuit where the stabilizer provides the necessary inductance. The resulting impedance characteristic is highly non-linear. If, however, a resistance R is introduced in series with the shunt capacitor, it can be adjusted so that the AC component of the current flowing through the anode series resistor encounters a low Q tuned circuit. The stabilizer with its compensating network then has low resistance over a wide range of frequencies. So did you understand that? Basically, these voltage reference valves, like that Zener, usually have a capacitor across them. It's only got 2 basic elements, a cathode and an anode. So from anode to cathode, it has usually a capacitor to stop it oscillating, to shunt AC frequencies to ground basically. What it's saying here, because of the impedance characteristic of this valve, if you just put a capacitor across it, there's a chance that this, with the capacitor, can basically form like a tank circuit that you get on, for oscillators, and it can oscillate, self-oscillate, parasitic oscillation. What we were getting very low frequency oscillation. I reckon it was something, it was lower than a hertz. It was a lot lower than a hertz. As you saw it going, 1 hertz maybe even less. Anyway, so go back over this way. This is complicated because our bloody valve is a VR150/30, but we're not quite sure whether it is. It could be a VR105, but wrongly labelled. We don't know. Anyway, this is the impedance frequency characteristics. This is a stabilizer impedance in ohms, 200 blah blah blah. And then what's that bloody curve there? It doesn't tell us, does it? So anyway, this is a curve. So basically what it's saying is, as the frequency goes up, the impedance goes up. And what it's telling you to do, it's telling you to put 120 ohm and a 250 nanofarad capacitor shunted across rather than just a capacitor. Thusly 120 and 250 nanofarads. Well, we ain't got a 250 nanofarads, we've got 220. So now then, 120 and 250 nanofarads gives us a cut-off frequency of 5.3 kilohertz. Well, that's a couple of capacitors, well, a capacitor and an RC filter. Bodged, not bodged in there, what am I on about? Yeah, well, they are sort of bodged. There was a bit of a sod to get the irons off. So there's a bit of a sod to get the iron in there. So anyway, we've got a 10 microfarad 350 volt from the grid, where do you call it, the control grid, to the 300 volt regulated supply. And then we've got a 220N and 140 ohm RC across the where do you call it, the voltage reference valve. Let's have a look at that and see if that's quietened things down a bit. From the last test that I did, it seems to have done. That's okay, because I think if this, I think this was responsible for all that low frequency fuckery that we had. Obviously if the screen grids are going boingy boingy boingy, everything else is going to go boingy boingy boingy. Right, there we go round the bleeding mulberry bush again then. Everything. Have I done anything stupid? We'll soon find out. Oh, nothing went bang, thank pretty fuck. Got a little bit of jiggery pokery on the output voltage, but I think that's because we've got no load. I'll set that when the amplifiers, what do you call it, I was looking at the footage of the VR tube that hopefully you should have seen earlier, where the glow was oscillating. That is no longer oscillating. This is, where are we, 0.50 millivolts per div, and we can't see anything. Let's bung the gain up. So now we're 5 millivolts per div. That's not bad. We've still got this weird sort of spurious sort of oscillation. As you can see, it's a bit unstable, but then again it's got no load on it, so that's a lot better than what we were getting. So now we'll try it with the amplifier. Oakley dokley, success of sorts. We've still got this sort of triangular, it's not quite triangular, but you know what I mean, waveform. This is the screen grid here. We've got no more oscillation, no more boinginess, which is good. Everything as far as I can see is in spec. We've got a bit of a weird thing with the supply for the protection circuit. Not sure what's going off there, but that's not a big issue at the moment. This is less than ideal. This translates to 7 millivolts RMS, which is, in the scheme of things, it's not a lot. It could be better. We might be able to improve that by putting more decoupling on there. I've just tacked a 47 microfarads across that 10 microfarads. It's improved it a little bit. Let's just have a look what that is in RMS. Sorry to jiggle you about a bit. I'll just point you over there, give you something to look at. Still got 7 millivolts, so that doesn't really improve things. Let's have a look at the output. Point Right, sorry, I'm really good at framing things. Right, this is the output. That's where we're not 50 millivolts. About 50 millivolts peak to peak sort of noise, according to this machine. Right, it's not on there, is it? One moment. Right, according to this, this is actually this HP8903B. Sorry, is it? Yeah, it is an 8903B. Keep forgetting. 13 millivolts, 50 hertz. So we might be able to. We can probably do something to reduce that, and it's still not bad. Got feedback applied. Frequency 1 kilohertz. Amplitude 0.02V. .3 volts RMS, 0.9% THD. Oh. .3 volts RMS. Distortion should have gone down yet. 0.3. That's about your normal sort of listening volume. I wonder now whether it'd be worth putting more feedback on there. Not sure. So everything seems to be a lot better. That's a hell of a lot better. We've got no instability. We can try the capacitive load again. God, there's some heat coming off these bloody 807s. Look nice though, don't they? Let me turn this off and then we'll just have a quick wrap up. So the cause of all that low frequency instability was the regulated power supply. I hadn't put this capacitor across here. I've got a 10 microfarad instead of 2 microfarads. I have got these big 600 volt 1 microfarad caps, but getting them in there is a bit nuts. Yeah, I got nothing like that. That's going to, on the schematic, on his schematic, he had a non-polarized capacitor to give you an idea. That's a 10 microfarad, 450 volts, non-polarized poly cap. That's going to just be a bit mad in there, isn't it? So let's just get back why that makes a difference. Basically, our grid of this error amplifier here, this going onto this ECC83 1 triode, comes off a potential divider that sets the grid at a certain voltage. I'm saying here 106 volts. Compares this to our voltage reference, which is 107. Because it's a potential divider and the cathode is basically connected between the two triodes, what happens there, this will try and compensate for it, thus feedback loop, keeping that at our steady 300 volts. When we didn't have that capacitor on there, I think this means that this grid now is just floating as far as AC is concerned. Yes, it's sitting at 106 volts DC, but as you know, there's any AC content on there will affect it, this triode, and thus will affect the control grid of series pass valve, and thus will affect our output. And because that flows back, we get a thing going backwards and forwards, hence we got that oscillation. This decouples that. So any AC current, so if we get a spike of voltage, the current, I think, on a capacitor lags, doesn't it, by 90 degrees, either lags or whatever. But any increase in voltage will result in a decrease of current, and this capacitor is already charged. So say if the voltage goes down, there's a stored charge on this capacitor, and so it will keep this at a steady AC voltage, is what I'm saying. I hope that makes sense. It basically decouples the AC, and it improves power supply rejection ratio. You see it used a lot on the Aikido, what's it, John Brodsky's where do you call it, a lot of his circuits, the Aikido circuits, he instead of putting the capacitor say from here to ground, he'll put it from the HT to the grid or whatever it may be on his circuits. So that's that. And yes, we also put an RC, I'm on the wrong ones in there, isn't it? We also put a RC filter across our voltage reference valve, meaning that it's basically got a nice steady AC sort of constant across quite a few frequencies, stopping it from self-oscillating. That's good. Everything looks good. Not a lot more to do now. I need to sort this protection circuit out. We've got, I'll go into that in another video. We've got like a 23 volt rail coming in which should go to this relay, and for some reason everything's good until everything's sort of powered up and then it drops. I'm not sure why. There might be a short somewhere. So I'm going to have a bit more of a play, go and bung it in the living room, have a bit more of a listen to it, because it is very easy to lose sight of things when you're just messing about and testing. Long video. Thank you very much for watching. Take care of yourselves. Ta-ra for now.